Hello, friend. Some nights, the universe whispers. October 19th, 2017. A telescope on a mountaintop in Hawaii saw something that shouldn't have been there. A streak of light moving wrong, too fast, too strange, not ours. For the first time in recorded history, something from beyond our solar system had come to visit. And we almost missed it. Before we begin, if you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. It helps this small corner of the universe grow one curious mind at a time. Now, let's drift. Tonight we'll follow the story of Oumuamua, a traveler from the space between stars. We'll walk through what scientists really discovered, what they still wonder about, and why this visitor changed everything we thought we knew about our place in the galaxy. You don't need to understand everything. Just rest and let the stars tell their story. The evening of October 19th, 2017 felt ordinary. It was autumn in Hawaii. The air was warm. The stars were beginning to appear. And on the summit of Haleakala, a mountain whose name means House of the Sun, a telescope was doing what telescopes do, watching, waiting, recording the night. The telescope was called Pan-STARRS 1. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. Scientists built it to hunt for asteroids that might one day threaten Earth. Every clear night, it scans the sky, methodically taking image after image, looking for anything that moves. That night, a postdoctoral researcher named Robert Warwick was reviewing images taken 6 days earlier on October 14th. He was looking for near-Earth objects, rocks that orbit close to our planet. Standard work, routine work. Then he saw it, a point of light, moving. But moving in a way that didn't make sense. Most asteroids orbit the sun in predictable paths like runners on a track. This thing wasn't running on any track we knew. It was moving too fast. And stranger still, when Warwick calculated backwards tracing where this object had come from, the math told him something extraordinary. It hadn't come from anywhere in our solar system. It had come from interstellar space, the vast darkness between stars. For 4 billion years, our solar system has been spinning through the galaxy, a small island of warmth in an ocean of cold. And in all that time, as far as we knew, nothing from outside had ever passed through. Or, if it had, we'd never noticed, until now. Scientists suggest that interstellar objects must exist. They've always assumed so. When solar systems form, they're messy. Planets migrate. Gravity throws rocks in every direction. Some of those rocks escape tumbling out into the galaxy to drift for millions, even billions of years. But seeing one, that was different. That was proof. Warwick knew immediately what he'd found. He also knew that time was not on his side. The object was already leaving, already racing away from the sun at incredible speed, 87.3 kilometers every second. That's about 195,000 miles per hour, faster than any spacecraft humans have ever built. Within hours, he sent out an alert. Astronomers around the world turned their telescopes toward this cosmic visitor. They had to work fast. They had maybe a few weeks at most before it would fade from view forever. They named it Oumuamua. The word comes from Hawaiian. It means scout or messenger. The name carries a double meaning, the first to arrive from afar reaching out. A scout sent ahead of others, still traveling through the dark. It's a beautiful name for something so strange. Think about what this means for a moment. Imagine you've lived in a house your entire life. You've watched your street, your neighborhood. You know every car, every face. And then one morning, someone walks past your window, someone you've never seen before. Someone who doesn't live on your street, doesn't live in your town, doesn't even live in your country. That's what Oumuamua was, a visitor from somewhere else entirely. But here's the thing that made this discovery so remarkable: we weren't ready. We almost missed it completely. Oumuamua was already inside our solar system when we spotted it. In fact, it had already made its closest approach to the sun on September 9th, more than a month before Warwick found it in the data. By the time we noticed, it was already on its way out. Why did it take so long? Partly because Oumuamua was faint. It wasn't glowing like a comet. It didn't have a bright tail. It was just a small dark object tumbling through space, reflecting only a tiny amount of sunlight. And partly because it came from a direction we weren't watching as carefully from above the plane where most planets orbit. It slipped past us like a shadow. Research shows that there may be thousands of interstellar objects passing through our solar system every year. Thousands. But they're moving so fast and they're so small and dark that we simply don't see them. Our telescopes weren't designed for this kind of hunt. Oumuamua was a gift of timing. It came close enough to the sun that its reflected light, though faint, was just bright enough for pan-stars to catch. What if Warwick had been looking at a different part of the sky that night? What if the weather had been cloudy? What if the telescope had been pointed just a few degrees in another direction? We would never have known it was there. Oumuamua would have passed through our solar system in silence like countless others before it leaving no trace. And we would still believe wrongly that we were alone in the cosmic dark, our solar system, an island with no visitors, no travelers, no proof that the space between stars is full of wandering things. But we did see it. And once the announcement went out, something extraordinary happened. Telescopes all over Earth swiveled toward this single point of light. Observatories in Hawaii, Chile, Arizona, Spain. The Hubble Space Telescope joined in. Radio telescopes listened for signals, though scientists didn't really expect to hear anything. For a few weeks, Oumuamua became the most watched object in the solar system. Every telescope that could see it did. Every scientist who could study it tried. Because this wasn't just a discovery. This was a first encounter. Humanity had met something that didn't belong to the sun. Think about the history of astronomy, thousands of years of watching the sky. Ancient civilizations tracked planets named constellations, predicted eclipses. Galileo turned his telescope toward Jupiter and saw moons. Herschel discovered Uranus. The Voyager probes reached the edge of our solar system. But never, not once in all that time, had we seen something from outside. We've imagined it, of course. Science fiction is full of visitors from other stars, ships probe signals. But this wasn't fiction. This was real. A real object from a real place far away. And yet, here's the strange part: we don't know where it came from. When scientists traced Oumuamua's trajectory backwards, they found it was moving roughly from the direction of the star Vega. Vega is one of the brightest stars in our night sky, part of the constellation Lyra. It sits about 25 light-years away. But Oumuamua didn't come from Vega. See, it's been traveling for a long time. A very long time. It seems as though it's been drifting through interstellar space for hundreds of thousands, maybe even millions of years, and stars move. Vega wasn't in that position 300,000 years ago. So, where did it start? What solar system gave birth to this wanderer? We don't know. The galaxy is old and space is vast. Oumuamua could have come from anywhere, a star that's long since died, a planetary system we'll never see, a place that existed when dinosaurs walked Earth. It carried no message, no markings, no signs, just silence and speed and strangeness. Now here's what makes this even more remarkable. Most people assume that scientists were able to study Oumuamua in detail, that we have clear images, close-up photos, data from every angle. We don't. Oumuamua was small, probably somewhere between 100 and 400 meters long, though even that's an educated guess. It was too far away and too faint for any telescope to photograph directly. What we saw was just a point of light, a single pixel in a vast image of stars. Everything we know about Oumuamua, its shape, its color, its motion, comes from watching how that point of light behaved. Scientists observed how its brightness changed as it tumbled through space. They measured the spectrum of light it reflected. They tracked its trajectory with exquisite precision, calculating how the sun's gravity pulled at it, how fast it accelerated where it was headed. From these tiny threads of data, they wove a picture of something extraordinary, something that didn't fit any pattern they knew. And that's where the mystery begins. Because the more scientists looked at Oumuamua, the stranger it became, it wasn't shaped like a normal asteroid, too elongated, too flat. It was tumbling in a complex way, spinning end over end every 7.3 hours. Its color was reddish, like old organic material baked by cosmic rays. And most puzzling of all, it was accelerating, moving faster than gravity alone could explain. Comets do this. When comets get close to the sun, ice on their surface vaporizes, jetting out gas that pushes them forward. But Oumuamua didn't look like a comet. It had no tail, no visible outgassing, no cloud of gas and dust around it. So, what was pushing it? Scientists suggested dozens of explanations. Maybe it was outgassing something invisible, hydrogen perhaps too faint to detect. Maybe the sun's light was pushing it the way wind fills a sail. Maybe it was shaped so strangely that radiation pressure could accelerate it. Or maybe, and this is where things get interesting, maybe it was something we'd never seen before. Some scientists wondered, could it be artificial? A probe from another civilization, a light sail pushed by starlight designed by minds we can't imagine. Not likely, most said, almost certainly not. But the question alone shows you how strange Oumuamua truly was. Strange enough that even cautious, careful scientists had to consider possibilities that sounded like science fiction. Because here's the truth, we've only been watching the sky with modern telescopes for a little over a century. We've only been able to detect interstellar objects for a few years. And in that tiny sliver of time, we found Oumuamua, something so unusual that we're still trying to understand it. What does that tell us about the universe? It tells us we're only beginning to see, that the space between stars isn't empty, that visitors come and go, silent and swift, and we've been blind to them until now. Oumuamua was the first, but it won't be the last. Right now, as you listen to this, Oumuamua is still out there. It's beyond the orbit of Neptune, racing outward at tens of thousands of miles per hour. It's already too faint for any telescope on Earth to see. We'll never spot it again. Never get another look. It came. It left. It asked more questions than it answered. And maybe that's what first contact looks like. Not a message, not a landing. Just a small dark object tumbling past us in the night, reminding us that the universe is wider than we thought. That we are not alone in the galaxy, not in terms of life necessarily, but in terms of travelers, things from elsewhere, visitors passing through. For 4 billion years, Earth orbited the sun, watching the same stars spinning through the same corner of space. And we thought we were isolated, safe in our little island of warmth and light. But we're not isolated. We're part of a vast river of matter rocks, ice dust, maybe even artifacts flowing through the galaxy. And sometimes, just sometimes, that river touches us. Oumuamua taught us that. It taught us to look up with new eyes, to watch for what doesn't belong, to wonder what else is out there tumbling through the dark, unseen and unnoticed. We thought we knew our neighborhood. Turns out we've been missing the visitors all along. And that changes everything. But this is just the beginning of the story. Because once scientists realized what they were looking at, once they understood that Oumuamua was truly from outside, they had to ask a harder question. A question that would lead them into deeper mysteries, stranger puzzles, and debates that still haven't ended. That question was simple. What exactly are we looking at? The thing about history is this. The most important moments often feel ordinary when they happen. Robert Varick wasn't expecting to change astronomy that night. He was doing paperwork, really reviewing old telescope images, checking data, looking for rocks that might threaten Earth someday. Standard Thursday work. And then he saw a dot that refused to make sense. Let's go back to that exact moment. October 19th, 2017, 10:10 p.m. Hawaii time. Werik was sitting at his computer at the University of Hawaii's Institute for Astronomy. The office was quiet. Most of his colleagues had gone home. He was scrolling through images taken by Pan-STARRS 1 on October 14th, 6 days earlier. The telescope takes 4 images of the same patch of sky, separated by about 30 minutes each. This technique helps scientists separate real moving objects from cosmic rays, satellite streaks, or camera glitches. If something appears in all 4 images and moves consistently, it's real. It's out there. Werik's software flagged one object, a faint point of light, moving. At first glance, it looked like an asteroid. Nothing special. Our solar system is full of asteroids, hundreds of thousands of them, tumbling through space, most minding their own business, in the belt between Mars and Jupiter. But when Werik ran the numbers, when he calculated the object's trajectory, something felt wrong. The orbit was hyperbolic. That's a technical term, but it means something profound. Most objects in our solar system travel in elliptical orbits, oval-shaped paths that loop around and around the sun forever. Planets do this. Asteroids do this. Even comets, most of them return eventually. But hyperbolic orbits are different. They're open-ended, one-way tickets. An object on a hyperbolic trajectory falls toward the sun, whips around it, and flies back out into space, never to return. Research shows that only a handful of objects in history had ever been observed with truly hyperbolic orbits, and all of them were comets born in the outer solar system, perturbed by gravity, sent careening inward and then back out. But when Werik traced this object's path backwards, the math told him something impossible. It hadn't come from the outer solar system. It had come from outside the solar system entirely. The velocity told the story. This object was moving at 26.33 kilometers per second relative to the sun before accounting for the sun's gravity. That's what astronomers call heliocentric velocity at infinity. It's the speed an object would have if the sun's gravity weren't pulling on it at all. Scientists suggest that anything moving faster than about 16.6 kilometers s relative to the sun, what's called solar escape velocity, cannot be gravitationally bound to our star. It's too fast. It will escape no matter what. This object was moving at 2633 kilometers s. It didn't belong here. It never had. Werik stared at his screen. He checked his calculations. Checked them again. Looked for errors in the software, glitches in the data, any reason why this couldn't be what it appeared to be. Everything checked out. He sent an email to his colleague Marco Micheli at the European Space Agency. The subject line was simple: possible interstellar object. Within hours, the message had spread. Astronomers across the world began pointing their telescopes at this single faint dot. The race was on. Here's what made the discovery so urgent time. Oumuamua, though it didn't have that name yet, was already leaving. It had made its closest approach to the sun on September 9th, more than a month before Werik spotted it. By the time humanity noticed, it was already 21 million miles from Earth and accelerating outward. Every day it was getting farther. Every day it was getting fainter. Telescopes around the world scrambled to observe it while they still could. The Gemini North Telescope in Hawaii, the Very Large Telescope in Chile, the Canada-France-Hawaii Telescope, NASA's Infrared Telescope Facility. Even the Hubble Space Telescope, normally reserved for deep space observations, turned its gaze toward this cosmic visitor. They had maybe 3 weeks, maybe 4 at most. After that, Oumuamua would be too faint to study a ghost retreating into darkness. Every observation mattered. Every data point was precious. And what scientists saw in those frantic weeks only deepened the mystery. The first question was simple: what does it look like? You might assume scientists could just take a picture, point a telescope, snap a photo, see what's there. But space doesn't work that way. Oumuamua was small, estimated between 100 and 400 meters long, That's about the length of 3 or 4 football fields. Sounds big, right? But remember, this object was millions of miles away. At that distance, even the most powerful telescopes on Earth couldn't resolve it as anything more than a single point of light. Think about it this way. If you stood in New York City and tried to see a football field in Los Angeles, not through a telescope, just with your eyes, that's roughly the scale we're talking about. You wouldn't see details. You'd barely see anything at all. So scientists had to get creative. They had to read the light. When you look at a distant star, you're not seeing the star itself. You're seeing the light it emits. And that light carries information. Its color tells you the star's temperature. Its brightness tells you its size or distance. Patterns in its spectrum reveal what elements are burning inside. Oumuamua didn't emit light. It reflected sunlight like the moon does. But that reflected light still carried secrets. Astronomers measured its brightness carefully, watching how it changed over time. And what they found was strange. Every 7.3 hours, Oumuamua brightened, then dimmed, then brightened again. The variation was dramatic, about 10 to 1. That means, at its brightest, it reflected 10 times more light than at its dimmest. Why does this matter? Because brightness variations tell you about shape and motion. If an object is perfectly spherical like a ball, it reflects the same amount of light no matter which way it's facing. But if an object is elongated like a cigar or a pancake, then as it tumbles, different amounts of surface area face the sun and the brightness changes. A 10 to 1 variation is extreme. It suggests Oumuamua was highly elongated, either very long and thin like a needle, or very flat and wide like a disc. Scientists ran the numbers. If Oumuamua was cigar-shaped, it would have to be at least 10 times longer than it was wide, maybe more. That's unusual, but not impossible. Some asteroids are elongated, but then in 2021, a team of researchers led by Yun Zhang proposed something different. They suggested Oumuamua might not be cigar-shaped at all. It might be pancake-shaped. Flat thin like a disc or a blade tumbling through space. Both shapes could produce the same brightness pattern. Both fit the data. We still don't know which is correct. We may never know. But here's the lesson. When you can't see something directly, you have to infer. You have to build models, test them against data. Accept that multiple answers might fit. Science isn't always about certainty. Sometimes it's about narrowing down possibilities. The second question was, what's it made of? Again, scientists couldn't collect a sample. They couldn't land on it, drill into it, bring back rocks to analyze. All they had was light. But light has color, and color reveals composition. When sunlight hits an object, some wavelengths are absorbed and others are reflected. Different materials absorb different colors. Ice reflects blue and white. Iron absorbs red and reflects gray. Organic molecules, carbon-based compounds, often reflect reddish hues. Astronomers measured Oumuamua's spectrum carefully. What they found surprised them. It was red. Not bright red, but a subtle organic red, similar to the color of objects in the outer solar system, like some asteroids in the Kuiper Belt or the surface of Pluto. Research shows that this kind of reddish color usually indicates the presence of organic molecules, carbon-based compounds that have been cooked by cosmic radiation over millions of years. When high-energy particles from space bombard organic materials, they break molecular bonds and create complex reddish residues called tholins. So scientists suggest Oumuamua's surface might be coated in tholins, ancient organic material baked by radiation during its long journey through interstellar space. But here's the strange part. Oumuamua was more reflective than most comets. Its albedo, the percentage of light it reflects, was higher than expected for a tholin-covered surface. That suggested something else might be going on. Maybe ice beneath the tholins, maybe a different kind of surface material altogether. Once again, the data pointed in multiple directions. Once again, scientists had to live with uncertainty. The third question, and perhaps the most important, was where did it come from? Not just from outside the solar system, But from where exactly astronomers traced Oumuamua's trajectory backwards, projecting its path through space like rewinding a film. They found that it had entered our solar system from roughly the direction of the star Vega in the constellation Lyra. Vega is one of the brightest stars in Earth's night sky, a brilliant blue-white star about 25 light-years away. For a moment, scientists wondered, could Oumuamua have come from Vega? But the answer, frustratingly, is no. Here's why. Oumuamua has been traveling for a very, very long time. Based on its velocity and trajectory, it seems as though it's been drifting through interstellar space for at least 300,000 years. Maybe longer. Maybe millions of years. And stars move. Vega wasn't in that part of the sky 300,000 years ago. It was somewhere else following its own orbit around the galaxy. So, Oumuamua didn't come from Vega. It only looks like it did because of how both objects have moved over time. Where then, scientists don't know. They may never know. The galaxy is old, stars drift, planetary systems form and die. Wherever Oumuamua was born, whatever sun once warmed it is lost to time. It's like finding a message in a bottle washed up on a beach. You can read the message, you can study the bottle, but you have no idea which shore it came from, or when it was cast into the sea. All you know is it traveled far, it traveled long, and now, by chance, it's here. Think about the timeline for a moment. Oumuamua may have been traveling for hundreds of thousands of years. While it drifted silently through the void, entire civilizations rose and fell on Earth. Humans evolved, built cities, invented writing, looked up at the stars and wondered. And all that time, Oumuamua was moving toward us slowly, patiently unaware and uncaring. It wasn't aimed at us. It didn't know we were here. It was just tumbling, following the gentle pull of distant stars, one lonely rock in an ocean of darkness. And then by pure chance, its path intersected ours. Scientists estimate that interstellar objects like Oumuamua pass through the inner solar system perhaps once a year, maybe more, maybe several times a year. But they're so small, so dark, so fast that we almost never see them. We saw this one because it came unusually close to the sun, close enough that its reflected light, though faint, was just barely bright enough to detect. If it had passed just a little farther out, we would have missed it entirely. If Pan-STARRS had been looking in a different direction, we would have missed it. If Robert Warwick had taken that night off, we would have missed it. But we didn't. And that single stroke of luck gave humanity its first confirmed glimpse of an object from beyond. Now here's a mistake people often make when they hear about Oumuamua. They assume scientists had weeks or months to study it in detail, that we could take our time, run experiments, gather all the data we needed. We didn't. By the time Oumuamua was discovered, it was already leaving. Astronomers had only a narrow window, about 11 days of useful observations, before it faded beyond the reach of Earth's most powerful telescopes. 11 days. That's all. In that short window, scientists had to coordinate observations across multiple continents, multiple telescopes, multiple wavelengths of light. They had to work fast, work carefully, and accept that many questions would remain unanswered. It's like trying to study a wild animal that walks past your window for 10 seconds. You see it, you take notes, you snap a few photos if you're lucky. But then it's gone, and you're left wondering, what was that? Where did it come from? Will I ever see it again? The answer to that last question for Oumuamua is no. By mid-November 2017, it had faded from view. By December, it was beyond the orbit of Jupiter, invisible to all but the most sensitive instruments. By early 2018, it was gone, too faint, too distant, lost in the vastness of space. We'll never see it again. Never get another chance. Everything we'll ever know about Oumuamua comes from those 11 days of frantic observation in October and November 2017. And yet, even with such a narrow window, scientists learned enough to realize something profound. Oumuamua wasn't just unusual. It was unlike anything we'd ever seen. Its shape, its color, its motion, all strange, all surprising, all difficult to explain using the models and theories that worked for every other asteroid and comet we'd ever studied. Which brings us to the question that would spark debates, headlines, and wild speculation for years to come. If Oumuamua doesn't fit the rules, what exactly is it? Sometimes the universe speaks in flickers. A point of light grows bright, then dim, then bright again. To most people, it's nothing just a star twinkling, a satellite passing. But to an astronomer, that flicker is a voice. It's telling a story about shape, about spin, about something tumbling through the dark. Oumuamua flickered, and what it said made no sense at all. When you can't see something directly, you learn to read shadows. You learn to listen to light. This is one of astronomy's oldest skills, inferring what's hidden by studying what's visible. We've used this technique for centuries. It's how we discovered that stars aren't eternal. They pulse, they dim, they die. It's how we found planets around other suns by watching starlight dip as worlds pass in front of them. And it's how scientists learned that Oumuamua was shaped like nothing we'd seen before. The key was something called a light curve. It sounds technical, but the concept is simple. You measure an object's brightness over time and plot it on a graph. Brightness on one axis, time on the other. The pattern that emerges tells you how the object is moving and what shape it might be. If an object is spherical like a ball, its brightness stays constant as it spins. Every angle reflects the same amount of light. The light curve is flat, unchanging. But if an object is elongated or irregular, the light curve dances. When the long side faces you, more surface area catches the sun and the object brightens. When the narrow end points toward you, less light reflects and it dims. Research shows that most asteroids have light curves that vary by a factor of 1.5 or maybe 2. A little brighter, a little dimmer, nothing dramatic. Oumuamua's light curve varied by a factor of 10. 10 times brighter at its peak than at its dimmest. That's extraordinary. That's a shape so elongated, so unusual, that some scientists initially thought there must be an error in the data. But there wasn't. Telescope after telescope confirmed it. Every 7.3 hours, Oumuamua brightened and dimmed in a smooth, predictable rhythm. It was tumbling end over end like a thrown stick spinning through the air. And whatever its shape, it was extreme. So the question became, what shape produces a light curve like that? The first model scientists proposed was simple. Oumuamua must be cigar-shaped, a long, narrow cylinder tumbling through space. If you imagine a pencil spinning in sunlight, you can picture it. When the long side faces the sun, the whole length reflects light bright. When the tip points toward you, only a small circle of surface is visible dim. Scientists ran the numbers. To produce a 10-to-1 brightness variation, Oumuamua would need to be at least 10 times longer than it was wide, maybe more. That would make it somewhere between 100 and 400 meters long and only 35 to 40 meters wide. In other words, shaped like a skyscraper lying on its side, tumbling through the void. It's not impossible. Some asteroids are elongated, but a 10-to-1 ratio. That's at the extreme edge of what nature usually produces. Most asteroids are lumpy, irregular, but roughly rounded. Gravity and collisions tend to break off the sharp edges. Over millions of years, rocks in space get smoother, more compact. But Oumuamua seemed to defy that pattern. It was too elongated, too strange. Then, in 2021, a team of researchers led by Yun Zhang from the University of Arizona proposed a different idea. What if Oumuamua wasn't cigar-shaped at all? What if it was flat? Not a cylinder, but a disc, a pancake, a blade tumbling edge over edge through space. Scientists suggest that a flat disc-like shape could also produce a dramatic light curve. When the flat side faces the sun, the entire surface reflects light bright. When the edge points toward you, only a thin sliver is visible dim. The math worked, the observations fit, and suddenly there were two plausible models. Two completely different shapes that could both explain the same data. We still don't know which is correct. Both are possible. Both are strange in their own way. But here's the lesson. When you're studying something you can't see clearly, you have to accept ambiguity. You have to build models, test them, and admit when multiple answers fit the evidence. Science isn't always about finding the right answer. Sometimes it's about narrowing down the possibilities and living with uncertainty. Now, let's talk about what that tumbling motion tells us. Oumuamua was spinning, rotating around its axis every 7.3 hours. But it wasn't spinning smoothly. It was tumbling, wobbling like a poorly thrown football spiraling through the air. This kind of motion is called non-principal axis rotation. And it's more complicated than simple spinning. Instead of rotating around one stable axis, the object tumbles chaotically, flipping end over end in a complex pattern. Why does this happen? Usually it means the object experienced some kind of violent event, a collision, an explosion, a close encounter with a planet that twisted and spun it. Something gave it a chaotic push, and now it's tumbling through space, slowly wobbling as it goes. Research shows that tumbling asteroids in our solar system often have histories of impacts. They were hit by something broken apart or spun up by a near miss with a larger body. But Oumuamua had been traveling through interstellar space for hundreds of thousands of years, maybe longer. Whatever caused its tumbling motion happened long, long ago. Perhaps it was ejected violently from its home solar system, spun wildly by a gravitational slingshot. Perhaps it collided with another object in the dark between stars. Perhaps it was always tumbling ever since it formed. We don't know. We can only watch the pattern of light and infer a story. What we do know is that 7.3-hour rotation period remained constant throughout the entire time we observed Oumuamua. It didn't speed up. It didn't slow down. Whatever forces shaped its spin had long since faded, and now it was coasting, tumbling quietly through the void, unchanged. It's a humbling thought. For hundreds of thousands of years, Oumuamua has been spinning in darkness, unseen and unknown. And for 11 brief days, we watched it flicker past a single glimpse of its ancient silent motion. But the light curve revealed something else, something that would become one of the deepest mysteries surrounding Oumuamua. The brightness variations were smooth, too smooth. Let me explain. Most asteroids aren't uniform. They have craters, ridges, valleys, uneven surfaces. When they tumble, their light curves show small bumps and irregularities, little deviations caused by shadows, by rough terrain, by uneven reflectivity. Oumuamua's light curve was smooth as silk, a perfect sinusoidal wave brightening and dimming in a clean, predictable rhythm with almost no irregularities. Scientists suggest this means one of two things. Either Oumuamua's surface was remarkably uniform, no large craters, no dramatic topography, just smooth, even material from end to end. Or the object was small enough that shadows and surface features didn't create visible variations at the distance we were observing from. Both options are strange. Both raise more questions. If the surface was smooth, why most objects in space are battered by impacts over millions of years? Smooth surfaces are rare. If the object was small, then the extreme brightness variation becomes even harder to explain. A small, smooth object shouldn't flicker so dramatically unless it's shaped like an impossibly thin needle or blade. Either way, Oumuamua was unusual. Every detail seemed to lead towards strangeness. Now, here's where things get really interesting. Let's talk about color. When sunlight hits an object, some wavelengths are absorbed and others are reflected. By measuring which colors come back, scientists can infer what the object is made of. Oumuamua reflected light in a distinctly reddish hue. Not bright red, but a subtle organic red, similar to the color of objects in the outer solar system, like some Kuiper Belt asteroids or the surface of Pluto. Research shows that this kind of color usually indicates the presence of organic molecules, specifically a class of compounds called tholins. Tholins are complex organic molecules that form when simpler carbon-based materials are bombarded by cosmic radiation over long periods of time. Think of it like this. If you leave organic material out in space for 1,000,000 years, high-energy particles, cosmic rays will slowly break apart the molecules and reassemble them into new reddish compounds. It's a form of space weathering, and it's common in the outer solar system, where the sun's warmth doesn't vaporize organic material. So, Oumuamua's red color suggested it was coated in Tholin's ancient organic material, baked and weathered by radiation during its long journey between stars. But here's the puzzle. Oumuamua was more reflective than most Tholin-covered objects. Its albedo, the percentage of light it reflects, was higher than expected. Typical comets have albedos of around 4%, meaning they absorb 96% of the light that hits them. They're dark, almost black. But Oumuamua's albedo was estimated at around 10%, maybe higher. That's still dark by everyday standards, but it's brighter than most comets. What does that mean? Scientists aren't sure. Maybe there was ice beneath the Tholins. Maybe the surface was a mix of materials, some dark, some bright. Maybe the tumbling motion exposed fresh, unweathered patches that reflected more light. Once again, the data pointed in multiple directions. Once again, the answer was, we don't know for certain. Let me pause here and talk about a common misconception. When people hear about Oumuamua, they often imagine that scientists have photographs, clear images showing its shape, its surface, its features. We don't. We never did. Every telescope that looked at Oumuamua saw the same thing, a single point of light, a pixel, a dot. All of our knowledge, the shape, the spin. The color comes from analyzing that dot, watching how bright it gets, how its color changes, how it moves across the sky. It's like trying to understand a person by watching their shadow on a distant wall. You can infer their height, their movements, maybe even their posture, but you never see their face. You never see the details. That's what studying Oumuamua was like. We saw a shadow, we read the flickers, and from those tiny threads of data, we wove together a picture of something strange and distant. But here's the beautiful part. Even from that single point of light, scientists learned so much. They learned it was tumbling. They learned it was elongated. They learned it was red-weathered ancient. They learned that the universe contains travelers we've never seen before, shapes we didn't expect, stories written in the language of light, waiting for someone patient enough to read them. Now you might be wondering, why does the shape matter so much? Why spend so much time analyzing brightness curves and rotation periods? Because shape tells you origin. Shape tells you history. If Oumuamua is a natural asteroid born in some distant solar system, ejected by gravitational interactions, then its shape should fit patterns we've seen before. Maybe unusual, but recognizable, within the boundaries of what collisions and gravity can create. But if the shape is too extreme, too thin, too flat, too smooth, then you start to wonder, could something else be going on? This is where the debates began. This is where scientists started to ask uncomfortable questions. Could Oumuamua's shape be natural, or could it be something designed? Not likely, most said. Almost certainly natural. But the question alone shows you how strange the data was. Because here's the truth. If you wanted to build a spacecraft that travels between stars, you wouldn't make it spherical. Spheres are inefficient. Too much mass, not enough surface area. You'd make it flat, thin, like a sail, like a blade, something that could catch light or magnetic fields or radiation pressure, something shaped to move. And Oumuamua's tumbling motion, that could fit too. A damaged probe spinning wildly after centuries of travel, or a natural object ejected violently from a dead solar system. Both explanations work. Both fit the flickers. Which brings us to the most controversial question. Oumuamua raised the question that would spark headlines, debates, and wild speculation. What was pushing it? In June 2018, 7 months after Oumuamua vanished from our telescopes, a team of scientists published something that changed everything. A paper, 12 pages, dense with mathematics and orbital calculations. And buried in the data was a discovery that made no sense. Oumuamua had been accelerating, not falling toward the sun, not coasting on momentum, accelerating away, pushed by something invisible. And no one could explain why. Gravity is predictable. That's one of the beautiful things about it. If you know an object's mass, its velocity, and the gravitational pull of nearby bodies, you can calculate its trajectory with extraordinary precision. You can predict where it will be a year from now, a century from now, a million years from now. This is how we track satellites, how we navigate spacecraft to distant planets, how we knew in 1705 that Halley's Comet would return in 1758, and it did right on schedule 16 years after Halley died. Gravity doesn't surprise us. Gravity follows rules. So, when scientists plotted Oumuamua's trajectory using observations from October and November 2017, they expected the math to work perfectly. They expected the object to follow a clean hyperbolic orbit falling toward the sun, whipping around it and shooting back out into space, pulled and pushed by gravity alone. But it didn't. Not quite. In June 2018, a team led by Marco Micheli at the European Space Agency published their findings in the journal Nature. The paper was titled Non-Gravitational Acceleration in the Trajectory of One-Eye 2017 U1 Oumuamua Non-Gravitational Acceleration. Those three words sparked a mystery that still hasn't been fully solved. What they found was this Oumuamua was moving slightly faster than gravity could account for. Not by much, just a tiny deviation, a small excess velocity. But it was real, it was measurable, and it was statistically significant. Research shows that when scientists say something is statistically significant, they mean it's not random noise. It's not a measurement error. It's a real effect detected across multiple observations confirmed by multiple telescopes. Oumuamua was accelerating. Something was pushing it, and whatever that something was, it wasn't gravity. Now, before we go further, let's talk about what acceleration means in space. On Earth, when we say something is accelerating, we usually mean it's speeding up a car, pressing the gas pedal, a ball falling faster as it drops. But in physics, acceleration is any change in velocity. Speeding up, yes, but also slowing down or changing direction. Anything that alters an object's motion. In space, most objects don't accelerate on their own. They coast. Once set in motion, they keep moving at the same speed and direction unless something pushes or pulls them. That's Newton's first law, inertia. Gravity is the main force that changes motion in space. Planets pull, the sun pulls, and objects respond by curving, falling, speeding up, or slowing down. But Oumuamua was doing something else. After accounting for the sun's gravity, Jupiter's gravity, and every other gravitational influence in the solar system, there was still a tiny acceleration left over, about 5 millimeters per second. That's incredibly small. If you were standing still and started accelerating at that rate, it would take you more than 50 hours to reach walking speed. But in space over weeks and months, even tiny accelerations add up. They change trajectories. They alter where an object ends up. And scientists noticed. They measured. They confirmed. Oumuamua wasn't just coasting. It was being pushed. So the question became, what could cause this acceleration? The first answer, the most obvious answer, is outgassing. This is what comets do. When a comet gets close to the sun, the heat vaporizes ice on its surface. Water, carbon dioxide, methane. All of it turns to gas and jets outward, creating the beautiful glowing tail we see in the night sky. But those jets don't just create a tail, they also push the comet. As gas streams off one side, the comet recoils in the opposite direction, like a balloon deflating and zipping around a room. Scientists have observed this effect hundreds of times. It's well understood. It's normal. So, when Micheli's team detected acceleration, the natural assumption was Oumuamua must be outgassing. It must be a comet. But here's the problem. Oumuamua didn't look like a comet. It didn't have a tail. It didn't have a visible coma, the fuzzy cloud of gas and dust that surrounds active comets. Telescopes searched carefully. The Hubble Space Telescope, the Spitzer Space Telescope. Some of the most sensitive instruments humanity has ever built looked for signs of outgassing. They found nothing. No tail, no coma, no dust, no detectable gas. And yet, something was pushing it. Scientists suggest several possible explanations. Let's walk through them carefully. First hypothesis: invisible outgassing. Maybe Oumuamua was releasing gas, but the gas was too faint to detect. Perhaps it was venting hydrogen, a gas that's invisible in most wavelengths, hard to observe, easy to miss. This idea gained traction in 2020 when two researchers, Daryl Seligman and Gregory Laughlin, published a paper proposing that Oumuamua might be a hydrogen iceberg. Here's how it works in the coldest parts of interstellar space. Hydrogen can freeze into solid ice. Not common, but possible. If Oumuamua formed in an extremely cold molecular cloud, temperatures close to absolute zero, its outer layers might be made of hydrogen ice. When it entered our solar system and got closer to the sun, that ice would sublimate, turn directly from solid to gas. Hydrogen gas is nearly invisible. It doesn't create a visible tail, but it would produce a gentle, constant push, exactly the kind of acceleration Micheli's team detected. The math worked, the physics fit, and it explained why we didn't see outgassing, because we were looking for the wrong kind of gas. But here's the catch. Hydrogen icebergs are fragile. They evaporate quickly. Scientists estimate that an object made of hydrogen ice shouldn't survive more than a few 100 million years in interstellar space before evaporating completely. Oumuamua appeared to be much older than that. Its surface was red-weathered, cooked by cosmic radiation. Signs of great age, not youth. So the hydrogen iceberg theory works, but it requires Oumuamua to be young, recently formed, born in a cold cloud, and sent on a journey that, by cosmic luck, brought it to our solar system before it evaporated. Possible, but unlikely. Second hypothesis: solar radiation pressure. This is the idea that light itself was pushing Oumuamua. It sounds strange, but it's real. Light carries momentum. When photons from the sun hit an object, they transfer a tiny amount of energy. For most objects, this push is negligible, far weaker than gravity. But for very small or very light objects, radiation pressure can matter. Think of a solar sail, a spacecraft design, where a huge thin sheet of reflective material catches sunlight, like a sailboat catches wind. Engineers have proposed using solar sails for interstellar travel because they require no fuel, just light. If Oumuamua was extremely thin, shaped like a blade or a pancake, as some models suggested, then solar radiation pressure might have been strong enough to accelerate it. But here's the problem: to make the math work, Oumuamua would need to be absurdly thin, less than a millimeter thick in some models. Essentially a cosmic sheet of paper tumbling through space. That's possible for an artificial object, a light sail perhaps. But for a natural rock, unlikely. Asteroids and comets aren't that fragile. Collisions would shatter them. Gravity would pull them into more compact shapes. So, solar radiation pressure could explain the acceleration, but only if Oumuamua was shaped in a way that nature rarely, if ever, produces. Strange. Not impossible, but strange. Third hypothesis: uneven heating. This is called the Yarkovsky effect, and it's subtle, but real. Here's how it works when the sun heats one side of an asteroid. That side becomes warm. Hours later, as the asteroid rotates, the warm side faces away from the sun and radiates heat into space. That radiated heat carries momentum, giving the asteroid a tiny push. It's like a very weak rocket engine powered by sunlight. Over millions of years, the Yarkovsky effect can change an asteroid's orbit significantly. Scientists suggest this might partially explain Oumuamua's acceleration. As it tumbled, different parts of its surface heated and cooled, creating tiny pushes that added up over time. But the numbers don't quite work. The Yarkovsky effect is too weak to account for the full acceleration Micheli's team observed. It might contribute, but it can't be the whole story. Fourth hypothesis, something we haven't thought of yet. This is always a possibility in science. Maybe Oumuamua's acceleration comes from a process we don't fully understand. A combination of effects, a material we've never encountered, a physical phenomenon we haven't studied closely enough. The universe is old, space is vast. We've been observing interstellar objects for less than a decade. It's entirely possible, likely even, that we're missing something. Science is comfortable with this. Good science is comfortable with saying, we don't know yet. But here's what makes Oumuamua so frustrating. Every explanation we've proposed has problems. Hydrogen ice requires youth. Radiation pressure requires extreme thinness. Outgassing requires gas we can't detect. The Yarkovsky effect is too weak. None of the natural explanations fit perfectly. And that's when scientists start to ask uncomfortable questions. Let me share a principle that guides scientific thinking. It's called Occam's razor, named after a 14th century philosopher, William of Ockham. The principle is simple. When you have multiple explanations for something, the simplest one is usually correct. Don't multiply assumptions unnecessarily. Don't invent complicated solutions when simple ones will do. Occam's razor is why scientists favor natural explanations over extraordinary ones. Hydrogen ice might be unlikely, but it's simpler than invoking alien technology. Solar radiation pressure might require an odd shape, but it's simpler than assuming Oumuamua is artificial. But here's the thing. Occam's razor doesn't mean the simplest explanation is always right. It means it's the best starting point. You test the simple ideas first, and if they all fail, if none of them fit the data, then you start considering more complex possibilities. That's where Oumuamua left us. None of the simple explanations worked perfectly. Every model had gaps. Every hypothesis had problems. And into that gap stepped a question that would dominate headlines, spark debates, and divide the scientific community. Could Oumuamua be artificial, not a rock, not a comet, but a probe, a craft, something designed? It sounds like science fiction. For most scientists, it is science fiction, an idea so unlikely that it's barely worth considering. But one scientist took it seriously. His name is Avi Loeb. He's a professor at Harvard, one of the most prestigious astronomers in the world. And in 2018, he published a paper suggesting that Oumuamua might be a light sail, a thin artificial structure built by an extraterrestrial civilization. The paper was careful, cautious. It didn't claim Oumuamua was alien. It simply said, we can't rule it out. The data fit. The acceleration, the shape, the lack of outgassing, all consistent with a damaged or derelict probe tumbling through space. The reaction was immediate. Some scientists praised Loeb for thinking boldly, for asking questions others were too cautious to ask. Others criticized him, saying he was sensationalizing weak evidence, encouraging wild speculation without sufficient proof. The debate raged. It still does. But here's what's important. The debate itself shows you how strange Oumuamua really was. Strange enough that serious scientists, people who've spent their careers studying the cosmos, had to consider possibilities they would normally dismiss. Because the truth is, we don't know what pushed Oumuamua. We measured the acceleration. We confirmed it was real, but we don't know the cause. And that uncertainty opens a door not to certainty, not to proof, but to wonder. To the possibility that the universe contains things we haven't imagined yet, visitors we weren't prepared for, questions we didn't know how to ask. So, what do we do with a mystery like this? How do we respond when the data doesn't fit? When every explanation has problems? When the universe whispers something we can't quite hear? We keep looking, we keep measuring, we build better telescopes, watch for more visitors, and gather more data. Because the next interstellar object might answer the questions Oumuamua raised, or it might deepen the mystery even further. What if we're not alone? What if just once something visited us? In November 2018, a scientist stood before the world's media and said something that made headlines everywhere. Oumuamua might be artificial, not a rock, not a comet, but a probe, a light sail sent by an alien civilization, now tumbling, broken through our solar system. Most scientists said no. One said maybe. And the debate that followed revealed something profound about how we search for truth when facing the unknown. His name is Abraham Loeb. People call him Avi. He's a professor of astronomy at Harvard University, one of the most prestigious positions in science. He's published hundreds of papers, advised dozens of students, served as chair of Harvard's astronomy department for nearly a decade. By any measure, he's not a fringe figure. He's establishment, credible, careful. Which is why, when he suggested Oumuamua might be artificial, the world listened. In November 2018, Loeb and his postdoctoral student, Shamuel Bialy, published a paper in the astrophysical journal Letters. The title was measured cautious. Could solar radiation pressure explain Oumuamua's peculiar acceleration? The paper didn't claim Oumuamua was alien. It didn't say we found a spacecraft. What it said was simpler, more careful. The data we have is consistent with an artificial origin. We can't rule it out. And maybe we should consider it. Research shows that when scientists say something is consistent with a hypothesis, they mean the evidence doesn't contradict it. It fits. It's possible. Not proven, but not impossible either. Loeb's argument was straightforward. He started with the acceleration, the mysterious push that couldn't be fully explained by outgassing or natural forces. Then he added the shape extremely elongated, possibly flat, like nothing seen before. And finally, the lack of a visible tail or coma despite being heated by the sun. All of this, he suggested, fits the profile of a light sail, a thin reflective sheet designed to catch starlight and use it for propulsion. Light sails aren't science fiction, they're real technology. Engineers on Earth have built small ones. Japan's Ikaros mission, launched in 2010, successfully used a light sail to travel through space. It works. The physics is sound. So, Loeb asked if humans can build light sails. Why not others? Why not some civilization, far older, far more advanced? And if such a civilization sent probes into the galaxy, thousands of them, millions drifting between stars, wouldn't some eventually pass through our solar system? Statistically, it's not impossible. It might even be likely depending on how common intelligent life is in the galaxy. And if one of those probes happened to tumble past us damaged or derelict after millions of years in space, wouldn't it look exactly like Oumuamua? No glowing lights, no transmissions, no intentional signals. Just an old broken machine spinning silently through the void. It fits. Not perfectly, but it fits. The response was immediate and intense. Within days, Loeb's paper had been downloaded thousands of times. News outlets around the world ran headlines. Harvard scientist says Oumuamua could be alien spacecraft. Talk shows called, podcasts invited him. The public was fascinated, but many of Loeb's colleagues were not. Scientists pushed back hard. Not because the idea of alien technology is inherently impossible. Most astronomers agree that intelligent life probably exists somewhere in the universe. But because they argued Loeb was elevating an extraordinary hypothesis without extraordinary evidence. This principle, extraordinary claims require extraordinary evidence, is a cornerstone of modern science. It was popularized by the astronomer Carl Sagan, though the idea is much older. The logic is simple, unlikely explanations need stronger proof than ordinary ones. If you hear hoofbeats, think horses, not zebras. If an object accelerates in space, think outgassing, not alien probes. Loeb's critics said yes, Oumuamua is strange. Yes, the acceleration is puzzling, but strange doesn't mean artificial. Puzzling doesn't mean designed. Nature is full of surprises, things we don't understand yet, things that don't fit our models. That doesn't mean we should jump to aliens. They proposed that the hydrogen iceberg theory, though imperfect, was still more plausible than invoking extraterrestrial technology, or that perhaps we simply don't understand Oumuamua's outgassing well enough, or that its shape, while unusual, could be explained by some rare but natural formation process we haven't studied closely. One astronomer, Paul Sutter, wrote, "We should exhaust every natural explanation before considering artificial ones, and we haven't exhausted them yet." Another, Catherine Mack, pointed out that we've only been observing interstellar objects for a few years. We don't know what normal looks like yet. Maybe Oumuamua seems strange simply because we have so little to compare it to. It's a fair point. If you'd only ever seen one tree in your life, you might think every tree looks the same. But see 100 trees and you'd realize they come in the countless shapes and sizes. Maybe Oumuamua is just the first of many strange visitors, all natural, all formed by processes we'll eventually understand. But Loeb didn't back down. In fact, he doubled down. He argued that science has a bias, a tendency to dismiss certain ideas not because the evidence is weak, but because the implications are uncomfortable. We are trained to be conservative, to favor conventional explanations, to avoid speculation that might damage our reputations. And that bias, Loeb said, might be holding us back. What if we're so afraid of being wrong about aliens that we ignore real evidence when it appears he pointed to history? In 1967, astronomers discovered pulsars, objects in space that emit perfectly regular radio pulses like cosmic lighthouses. The signals were so precise, so rhythmic, that some scientists briefly wondered if they were artificial. They even nicknamed the first one LGM-1 for Little Green Men. Of course, pulsars turned out to be natural, rapidly spinning neutron stars, their magnetic field sweeping across space like a beacon. Not aliens, just physics. But the point is, scientists considered the possibility. They tested it. And when the evidence pointed toward a natural explanation, they accepted it and moved on. Loeb argued that's all he was doing with Oumuamua, not claiming it's alien, just saying, let's consider it, let's test the hypothesis, let's be open to possibilities, even uncomfortable ones. Because the truth is, we don't know how common intelligent life is in the universe. We don't know how often civilizations arise, how long they last, or whether they send probes into the galaxy. We have theories, guesses, equations, but no data, no confirmed examples. Just us alone on Earth wondering. And until we look, until we actively search carefully and scientifically, we'll never know. This is where the story gets interesting, because Loeb didn't just publish a paper and walk away. He helped launch a project to search for evidence. It's called the Breakthrough Listen Initiative, funded by the billionaire Yuri Milner. The goal is simple: use the world's most powerful radio telescopes to listen for signals from extraterrestrial civilizations. When Oumuamua was first discovered, Breakthrough Listen turned its attention toward this mysterious visitor. For 10 hours on December 13th and 14th, 2017, the Green Bank Telescope in West Virginia, one of the largest radio telescopes on Earth, listened carefully. It scanned across a wide range of frequencies from 1 to 12 gigahertz, searching for any signal that might indicate technology, radio transmissions, electronic noise, anything artificial. The telescope was so sensitive that if Oumuamua had been transmitting with even a tiny amount of power, roughly equivalent to a cell phone, Green Bank would have detected it. Scientists analyzed the data carefully. They looked for patterns, for anomalies, for anything out of place. They found nothing. No signals, no transmissions, just silence. Does that prove Oumuamua isn't artificial? Not necessarily. A broken probe wouldn't transmit. A derelict spacecraft damaged and dead would tumble silently just like Oumuamua did. But it does mean we found no evidence of technology, no smoking gun, no proof. Just a strange object moving in a strange way, leaving us with questions. Now, let's talk about why this debate matters. Why it's not just academic squabbling, but something deeper. Science works by testing ideas. You propose a hypothesis, gather evidence, and see if the data fits. If it doesn't, you revise the hypothesis or discard it. If it does, you keep testing, keep refining, until you're as certain as you can be. But what happens when the data is ambiguous? When multiple hypotheses fit equally well? When you don't have enough information to choose? That's where Oumuamua left us. Hydrogen iceberg possible, light sail possible, unknown, natural process possible. All three explanations have problems. All three require assumptions. None can be proven with the data we have. So, how do scientists decide? Most fall back on Occam's razor. Choose the simplest explanation. Favor the natural over the artificial. Don't multiply assumptions unnecessarily. But Loeb argues that sometimes Occam's razor can mislead us. Sometimes the simple explanation is only simple because it's familiar. And sometimes reality is stranger than we expect. He likes to quote Sherlock Holmes, "When you have eliminated the impossible, whatever remains, however improbable, must be the truth." The problem is we haven't eliminated anything yet. With Oumuamua, everything remains on the table, improbable perhaps, but not impossible. There's a deeper question here, one that goes beyond Oumuamua. It's a question about how we search for life beyond Earth. For decades, scientists have been listening for radio signals from the distant civilizations. Programs like SETI, the search for extraterrestrial intelligence, scan the skies, constantly hoping to catch a message, a pattern, a sign that someone out there is trying to communicate. So far, we've heard nothing. Decades of listening, and the universe remains silent. But what if we're listening for the wrong thing? What if alien civilizations don't broadcast radio signals? What if they communicate in ways we haven't imagined or stopped transmitting millions of years ago? Research shows that intelligent civilizations, if they exist, might be rare, brief, or quiet. They might arise, flourish, and vanish long before their signals reach us. Or they might use technologies we can't detect, strategies we haven't thought of. And if that's true, then maybe the best way to find them isn't by listening. Maybe it's by looking, searching for artifacts, physical objects, probes sent into the galaxy to explore, to gather data, to drift between stars long after their creators have gone. This idea is called the search for techno-signatures, not radio signals, but physical evidence of technology. Megastructures around stars, industrial pollution in planetary atmospheres, or, yes, light sails tumbling through our solar system. Loeb argues that Oumuamua, whether natural or artificial, should remind us to look for these things, to take the search for techno-signatures seriously, to accept that if intelligent life exists, its traces might be subtle, ambiguous, easy to miss, and maybe we've already seen one. We just can't prove it yet. Here's a question worth sitting with. How would you know if you'd found evidence of alien technology? Think about it. If a probe from another civilization passed through our solar system, old, broken, silent, what would distinguish it from a natural object? Shape. Maybe, but nature creates strange shapes too. Acceleration. Maybe, but we don't fully understand all the forces acting on interstellar objects. Composition. Maybe, but alien materials might resemble natural ones, especially after millions of years of weathering. The truth is, proving something is artificial is incredibly hard without context. Without signals, without markings, without clear signs of design, you're left guessing. And that's the position Oumuamua left us in. We saw something, we measured it, we analyzed it. And in the end, we couldn't say for certain what it was. That ambiguity frustrates some people. They want answers clear, definitive, certain. But science doesn't always provide certainty. Sometimes the most honest answer is, we don't know yet, and maybe that's okay. Maybe the mystery is what matters. The fact that we're asking the question at all, the fact that we're looking up, wondering, considering possibilities we once thought were impossible. Because whether Oumuamua is a rock and iceberg or a light sail, one thing is certain: it changed how we think about our place in the universe. For the first time, we saw an object from beyond. For the first time, we had to ask, could this be a message? Could this be contact? The answer most likely is no, probably not, almost certainly not. But we asked. And that question, that willingness to wonder, is what makes us human, what makes us scientists, what keeps us looking up at the night sky even when the universe stays silent. So, what does the data actually tell us? Strip away the speculation, the headlines, the debates. What do we really know about Oumuamua? What can we say for certain, and what remains beyond our grasp? After all the speculation, all the headlines, all the debates about aliens and light sails and hydrogen ice, there's one question that matters most. What do we actually know? Strip away the theories, set aside the arguments. What did Oumuamua tell us in its own silent language of light and motion before it disappeared forever? The answer is both simple and profound, more than we expected and far less than we hoped. Let's start with what we know for certain facts so well established that no scientist disputes them. First, Oumuamua came from outside our solar system. This isn't speculation. It's confirmed by the mathematics of its trajectory. When astronomers calculated Oumuamua's orbit, they found it was hyperbolic, an open curve, not a closed ellipse. Its velocity, even accounting for the sun's gravity, was too high to be bound to our star. It was passing through, not orbiting. Research shows that an object's orbital energy determines whether it's bound to a gravitational system. Negative energy means it's trapped orbiting forever. Positive energy means it's free traveling on a one-way path. Oumuamua's orbital energy was positive, strongly positive. No matter how you calculated it, no matter which model you used, the answer was the same: this object didn't belong to the sun. It never had. That makes it the first confirmed interstellar object ever detected passing through our solar system. Not the first to pass through, there have probably been millions over billions of years, but the first we ever saw. That alone is extraordinary. That alone changes everything. Second, Oumuamua's trajectory can be traced, but not to a specific origin. When scientists ran the numbers backwards, projecting where Oumuamua came from, they found it arrived from the general direction of the constellation Lyra near the bright star Vega. But as we've discussed, Vega wasn't in that position when Oumuamua began its journey. Stars move, the galaxy rotates, everything drifts. Based on Oumuamua's velocity, about 26 kilometers per second, relative to the local standard of rest, scientists estimate it's been traveling for hundreds of thousands of years. Maybe longer, maybe much longer. That's a long time. Long enough for its birthplace to be lost. Long enough for the star it once orbited, if it ever orbited a star, to have moved far away, or died, or become unrecognizable. We can say where it came from in a general sense, somewhere in the Milky Way, somewhere beyond our solar system. But the specific star, the specific planetary system, unknown. Unknowable with the data we have. It's like finding a leaf floating in the ocean. You know it came from land. You know it fell from a tree. But which shore, which forest, which tree? The ocean keeps those secrets. Third, Oumuamua was small, dark, and red. We never resolved it as more than a point of light, but by measuring its brightness and color, scientists estimated its size and composition. It was probably between 100 and 400 meters long, about the length of a few city blocks. Maybe smaller, maybe larger, depending on how reflective its surface was. Its albedo, the percentage of light it reflected, was estimated at around 10%. That's dark. Not as dark as charcoal, but darker than most rocks on Earth. Darker than most asteroids, though, similar to some comets. And its color was distinctly red. Not bright red, but a subtle organic red, the kind of hue you see in old weathered materials that have been exposed to cosmic radiation for millions of years. Scientists suggest this reddish color indicates the presence of Tholin's complex organic molecules formed when simpler carbon-based compounds are bombarded by high-energy particles in space. Tholins are common in the outer solar system. They coat the surface of Pluto, give some asteroids their ruddy hue, and appear on ancient comets. They're a sign of age of long exposure to the harsh environment of space. So, Oumuamua's color told a story. This object was old. It had been traveling for a very long time, long enough for its surface to be cooked, baked, transformed by radiation. But what it was made of underneath ice rock metal, we don't know. The color tells us about the surface, but the interior remains a mystery. Fourth, Oumuamua was tumbling, not spinning cleanly. Every 7.3 hours, its brightness changed, dramatically brightening by a factor of 10, then dimming again in a smooth, predictable rhythm. This told scientists two things. First, the object was elongated or flat-shaped in a way that reflected more light from one angle than another. And second, it was tumbling in a complex motion, not spinning smoothly around a single axis. Scientists call this non-principal axis rotation. It's the kind of motion you see when something has been disturbed, hit by an impact, spun by a gravitational encounter, or ejected violently from its home system. Whatever caused Oumuamua's tumbling motion happened long ago. The tumbling rate didn't change during the time we observed it. It was stable coasting, spinning the same way it probably had been for thousands or millions of years. That's one of the strange things about space. Once an object is set in motion, there's nothing to slow it down, nothing to change it, no air resistance, no friction, just silence and inertia. Oumuamua was spinning when it entered our solar system, and it's still spinning now, somewhere beyond Neptune, tumbling quietly through the dark. Fifth, Oumuamua experienced non-gravitational acceleration. This is the detail that sparked the most debate. As Oumuamua moved away from the sun, it accelerated slightly, not much, just a tiny push, but measurable and real. Scientists confirm this by tracking its position over several weeks and comparing the observed trajectory to the predicted one. The difference was small, but statistically significant. Something was pushing it. The acceleration was strongest when Oumuamua was closest to the sun, then gradually weakened as it moved farther away. That pattern is consistent with a force related to sunlight or solar heating, something that gets weaker with distance. But here's what we don't know what caused it. Was it outgassing radiation pressure? Some unknown process the data doesn't tell us. It only tells us the acceleration happened. And that ambiguity, that gap between what we measured and what we can explain, is where all the speculation lives. Hydrogen ice light sails, exotic materials, unknown physics. All of these are attempts to fill the gap. But the gap remains. We measured the effect. We don't fully understand the cause. Sixth, Oumuamua showed no detectable outgassing. When telescopes looked for a tail, a coma, a cloud of gas or dust around Oumuamua, they found nothing. No visible sign of material streaming off its surface, even though it passed close enough to the sun to be heated significantly. This is unusual. Most comets, when heated, produce visible tails. The ice vaporizes, the gas glows, and we see it from Earth as a beautiful glowing cloud. Oumuamua didn't do that. Or if it did, the outgassing was too faint to detect, perhaps because the gas was invisible like hydrogen, or because the amount was too small to see from Earth. Research shows that the absence of detectable outgassing doesn't mean there was no outgassing. It just means we couldn't see it. There's a difference. But it's still unusual. It's still something that sets Oumuamua apart from most comets we've studied. Seventh, Oumuamua moved fast and left quickly. Its velocity relative to the Sun before accounting for gravitational acceleration was about 26.3 kilometers per second. That's fast. Faster than anything bound to our solar system could move without help. To put that in perspective, Voyager 1, the fastest human-made object to leave the solar system, is moving at about 17 kilometers per second. Oumuamua was moving 50% faster, and it didn't need a rocket to get there. That was just its natural speed, the velocity it carried with it from interstellar space. When it entered our solar system in early September 2017, it fell toward the Sun, accelerated by gravity, whipped around the star, and shot back out again. The entire encounter lasted only a few months. By the time we discovered it in mid-October, it was already leaving. By December, it was beyond Jupiter. By early 2018, it was too faint to see. We'll never see it again. It's gone racing outward at tens of thousands of miles per hour, heading toward the constellation Pegasus. In about 20,000 years, it will pass near another star, then another, and we'll never know where it goes or what it sees along the way. Now here's what we don't know, and this list is long. We don't know where Oumuamua was born. We don't know how old it is. We don't know what it's made of, rock, ice, metal, something else. We don't know its exact shape. We don't know what caused its acceleration. We don't know if it's one of a kind or if objects like it are common in interstellar space. We don't know if it was ever part of a planetary system or if it formed in isolation in some cold cloud between stars. We don't know if it's been traveling alone for its entire existence or if it once had companions, other rocks, other wanderers, all scattered long ago by some violent event. We don't know if it will survive forever, slowly eroding under the pressure of cosmic rays, or if it will one day collide with something, a star, a planet, another wandering object, and shatter into dust. We don't know its story. We only know one brief chapter, the time it spent passing through our little corner of the galaxy, 11 days of frantic observation, before it faded into darkness. That's all. That's what we have. Let me share something important about science. People often think science is about certainty, about finding the right answer, proving things beyond doubt, building a perfect map of reality. But that's not quite true. Science is about reducing uncertainty. It's about gathering evidence, testing ideas, and narrowing down possibilities. Sometimes you find the answer. Sometimes you just rule out the wrong ones. With Oumuamua, we ruled out a lot. We know it's not from our solar system. We know it's not a typical asteroid or comet. We know it moved in a way that defies simple explanation. But we couldn't narrow it down to one answer. The data fit multiple models. The evidence pointed in several directions. And in science, when that happens, you accept it. You say we don't know yet. We need more data. We need more observations. We need more visitors like this one, so we can compare, contrast, and find patterns. That's the position Oumuamua left us in. Humbled, curious, waiting. There's a lesson here about the limits of knowledge, about how much we can learn from a single glimpse of something distant and fleeting. Imagine you're standing in a field at night, and for just a moment, a bird flies past, silhouetted against the stars. You see it for a second, maybe two, and then it's gone. Could you identify the species? Probably not. Could you tell if it was healthy or where it came from or where it's going? Almost certainly not. But you'd know you saw something. You'd know birds exist. And if you'd never seen a bird before, if you'd spent your whole life thinking the sky was empty, that single glimpse would change everything. That's what Oumuamua did. It changed everything not by giving us answers, but by showing us that the space between stars isn't empty, that visitors pass through, that we live in a galaxy full of wandering things, most of which we'll never see. That single glimpse was enough, not to satisfy us, not to answer every question, but enough to show us that the universe is stranger, fuller, and more interesting than we thought. So, what do we do with incomplete knowledge? How do we respond when the data runs out before the mystery does? We keep watching. We build better telescopes, tools that can spot visitors earlier, track them longer, study them in more detail. We prepare for the next encounter knowing that Oumuamua wasn't the last. It was just the first we saw. Because the truth is, interstellar objects are probably common. Astronomers estimate that several pass through the inner solar system every year, maybe more. We just haven't been looking carefully enough to see them, but that's changing. New survey telescopes are coming online, like the Vera Rubin Observatory, which will scan the entire visible sky every few nights, hunting for anything that moves. When it starts operating, we'll see more. Not just one Oumuamua, but dozens, maybe hundreds. Enough to find patterns, enough to understand what's normal and what's strange. And maybe in that flood of data, we'll finally understand what Oumuamua was. Not by studying it directly, we can't, it's gone, but by seeing others like it. By building a catalog of interstellar visitors and learning their language. That's the hope. That's what Oumuamua started. Not an answer, but a search. A new way of looking at the sky with eyes open for travelers from beyond. But even as we prepare for the next visitor, Oumuamua's story raises a deeper question. Are we alone in seeing these travelers? Or is the galaxy full of eyes watching? Wondering, seeing the same strange visitors pass through their skies? 2 years after Oumuamua vanished, something else appeared. August 30th, 2019. Another telescope, another faint point of light, another object moving wrong. And this time, scientists knew exactly what they were looking at, a second visitor from beyond. We are not alone in the galaxy, and the travelers are just beginning to arrive. His name was Gennady Borisov, an amateur astronomer working at his own observatory in Crimea. Not a government facility, not a university lab, just a backyard telescope, and a man who loved watching the sky. On the night of August 30th, 2019, Borisov was conducting a routine survey scanning for comets when he noticed something unusual, a faint fuzzy object moving across his images. At first, he thought it might be a known comet, but when he checked the databases, nothing matched. He reported it. Within days, other astronomers confirmed his discovery, and within weeks, the calculations came back. This object, like Oumuamua, was on a hyperbolic trajectory. It was moving too fast to be bound to the sun. It came from interstellar space. A second visitor. Scientists named it 2I Borisov, the 2I, meaning second interstellar object. And unlike Oumuamua, this one was obvious. This one looked exactly like what it was, a comet. It had a tail, a bright glowing coma of gas and dust. It was outgassing, visibly releasing water vapor, carbon monoxide, and other familiar molecules as the sun heated its icy surface. Research shows that 2I Borisov behaved like comets from our own solar system, similar composition, similar activity, similar brightness patterns. If you'd shown an astronomer images of 2I Borisov without context, they might have assumed it was a local comet born in our Oort cloud, making its first pass around the sun. But it wasn't. It was an interloper, a visitor, just like Oumuamua. And that's when scientists realize something profound: interstellar objects aren't rare. They're not once-in-a-lifetime events. They're common. They pass through our solar system regularly, maybe several every year, and we've only just started noticing them. Let's talk about the difference between Oumuamua and 2I Borisov, because it's revealing. Oumuamua was strange, no-tail odd shape, mysterious acceleration, red and weathered. It defied easy explanation. It sparked debates, wild theories, endless speculation. 2I Borisov was normal. It looked like a comet, behaved like a comet, and fit every model scientists had for how comets should act. Its composition matched what you'd expect from a chunk of ice and rock formed in the outer regions of a distant planetary system. Scientists studied 2I Borisov carefully. They measured its coma, analyzed its spectrum, tracked its outgassing. They found water, carbon monoxide, and cyanide molecules common in comets from our own Oort cloud. They even detected traces of nickel and iron in its coma, which was surprising. Most comets don't show metals in their gas. But 2I Borisov did, suggesting its composition might be slightly different from local comets, perhaps, formed in a colder, more metal-rich environment around another star. But overall, normal, familiar, comfortable. And that's the lesson. Oumuamua wasn't typical. It was the outlier. 2I Borisov showed us what a normal interstellar object looks like, and it looks like home. So the question becomes, if 2I Borisov is normal, what was Oumuamua? Maybe it was unusual even among interstellar objects. Maybe it came from a different kind of system, a place where comets don't form the same way, where ice doesn't coat rocks, where conditions are stranger than anything we've seen. Or maybe we just caught it at a different stage of its life. 2I Borisov was active outgassing fresh. Oumuamua was old-baked, weathered its surface, coated in tholins, its ice long since depleted or buried deep beneath a crust. Either way, 2I Borisov taught us that interstellar visitors come in at least two flavors, the familiar and the strange. And we can't assume every visitor will look like the first one we saw. Now, let's talk numbers. How common are these visitors? Before Oumuamua, scientists could only guess. They built models based on theory: how often planets eject material, how many rocks get thrown into interstellar space during solar system formation, how long objects survive before colliding with something or being pulled into a star. The estimates varied wildly. Some models suggested a few interstellar objects pass through the inner solar system per year. Others suggested dozens. A few optimistic models suggested hundreds, but we had no data, just guesses. Then we found Oumuamua and 2I Borisov within 2 years of each other. That's 2 confirmed detections in a very short time, using telescopes that weren't even designed to hunt for these objects. Scientists ran the statistics. Based on how much sky we were surveying, how sensitive our telescopes were, and how many objects we detected, they estimated that interstellar objects probably pass through the inner solar system inside the orbit of Neptune several times per year. Maybe 5, maybe 10, maybe more. Research shows that for every interstellar object we detect, there are probably hundreds or thousands we miss, objects that pass too far from the sun to brighten enough or move through regions of sky we're not watching or simply fade before we notice them. The galaxy, it seems, is full of wanderers. Billions upon billions of rocks, ice chunks, and debris, all thrown out of their home systems, all drifting through the dark, all occasionally passing through other solar systems by pure chance. We live in a cosmic crossroads, a place where paths intersect, and we've only just started paying attention. Here's what that means. For the future, we're about to see a lot more visitors. Right now, new telescopes are coming online, instruments specifically designed to scan the entire sky, repeatedly hunting for anything that moves. The most important is the Vera C. Rubin Observatory, currently being built in Chile. When it begins full operations, it will photograph the entire visible sky every few nights, creating a constant high-resolution movie of the heavens. It's designed to catch transient events, supernovae, asteroid impacts, anything that changes. But it will also be perfect for finding interstellar objects. Scientists estimate that once Rubin starts operating, we'll detect dozens of interstellar visitors every year, maybe hundreds. Enough to study them statistically, enough to understand their diversity, enough to map the currents and flows of debris moving through the galaxy. We'll learn which types are common and which are rare. We'll see if Oumuamua-like objects are 1 in a million, or if they're just hard to spot. We'll discover new categories, shapes, and compositions we haven't imagined yet. And maybe we'll find something truly extraordinary. An object so strange, so clearly artificial, that even the most skeptical scientists will have to admit we're not alone. But that's the future. For now, we have 2 visitors, 2 data points, just enough to know that more are coming. Let me tell you about a mission that almost happened. In 2017, after Oumuamua was discovered, a group of scientists proposed a bold idea: send a spacecraft to catch it. Not just observe from afar, but actually chase it down, match its speed, and study it up close. They called it Project Lyra after the constellation Oumuamua appeared to come from. The plan was audacious. Oumuamua was already leaving the solar system at incredible speed. To catch it, a spacecraft would need to accelerate faster than anything humans have ever launched, using gravitational slingshots around Jupiter, advanced propulsion systems, maybe even experimental technologies like solar sails or nuclear rockets. The mission would take years, maybe decades. The spacecraft would have to travel farther than any probe has gone, chasing a target that's tumbling dark and impossibly distant. But if it worked, if we could reach Oumuamua, we'd learn everything. We'd photograph it, measure it, maybe even land on it, drill into its surface, analyze its composition directly. We'd know once and for all what it was: rock or ice, natural or artificial, ancient wanderer or silent probe. The project was studied seriously. Engineers ran the numbers, physicists designed trajectories. But in the end, it was too expensive, too risky, too far beyond current technology. Project Lyra remains a dream, a what if, a reminder that sometimes the universe moves faster than we can follow. But here's the important part. The idea isn't dead. It's just waiting for the next visitor, the next Oumuamua, the next chance. Because now we know they're coming. Now we know to watch. And next time, maybe next time, we'll be ready. There's another mission in the works, one that might actually fly. It's called the Comet Interceptor. Unlike most space missions which target known objects years in advance, the Comet Interceptor will wait. It will launch without a specific destination, park itself in a stable orbit, and watch. And when something interesting appears, a new comet, an interstellar visitor, anything unusual, it will wake up, change course, and intercept it. The European Space Agency approved the mission in 2022. If all goes well, it will launch in the late 2020s, ready to respond to whatever the universe sends our way. Scientists suggest this is the future of interstellar object research flexibility. Instead of planning missions years in advance, we build spacecraft that can react quickly, chase targets of opportunity, and adapt to discoveries we haven't made yet. Because the truth is, we don't know what's coming next. We don't know if the next visitor will be a comet like 2I Borisov, or something strange like Oumuamua, or something entirely new. But we'll be watching. And when it arrives, we'll be ready to learn everything it has to teach us. Now, let's talk about what these visitors mean for our understanding of the galaxy. For most of human history, we thought of solar systems as isolated, each one a separate island spinning alone in the dark. Stars might be neighbors gravitationally, but their planetary systems didn't interact. No exchange of material, no shared history, just distance and silence. Oumuamua and 2I Borisov changed that. They showed us that solar systems aren't isolated. They're connected loosely through a slow exchange of debris. When planets form, they throw rocks everywhere. When stars pass close to each other, they stir up comets from distant clouds. When a star dies or a planetary system becomes unstable, material is ejected, sometimes gently, sometimes violently, into the galaxy. All of that material drifts. Some of it falls into other stars, some collides with planets, and some by chance passes through systems like ours, silent travelers carrying stories we can barely read. Research shows that this process has been happening for billions of years. Every solar system in the galaxy is constantly ejecting material and receiving visitors from elsewhere. It's a slow churn, a cosmic mixing invisible unless you're watching carefully. And here's the profound part: some of that material might be carrying life. Not intelligent life, not aliens waving hello, but microbes, bacteria, hardy organisms frozen in ice, drifting through space, surviving the cold and radiation for millions of years. Scientists call this panspermia, the idea that life might spread between worlds not through intentional seeding, but through natural processes. A rock gets ejected from a planet, with life drifts through space, eventually lands on another planet. And if conditions are right, the dormant organisms wake up and start reproducing. It sounds like science fiction, but it's scientifically plausible. We know some microbes can survive extreme conditions. We know rocks are ejected from planets. We know interstellar travel happens naturally. Could Oumuamua have been carrying life? Almost certainly not. It was too hot, too baked by radiation, too old. But 2I Borisov, a fresh comet full of ice protected from radiation. Maybe, just maybe, we didn't get close enough to check, but next time we might. Here's a question worth considering. If interstellar visitors are common, why did it take until 2017 to find one? The answer is simple: we weren't looking. Not carefully enough. Not with the right tools. Most telescopes are designed to study distant objects, galaxies, stars, nebulae. Things that stay still or move so slowly that their motion is barely noticeable. Interstellar objects move fast. They streak across the sky, visible for weeks or months before vanishing forever. To find them, you need wide-field telescopes that scan large areas of sky, repeatedly comparing images to spot anything that moves. You need automated software that can flag unusual trajectories. You need astronomers ready to follow up quickly before the object fades. Pan-STARRS. The telescope that found Oumuamua was built to hunt for near-Earth asteroids rocks that might someday threaten our planet. Finding an interstellar visitor was a bonus, a stroke of luck. But now, knowing they exist, knowing they're common, we're building telescopes specifically to find them. Rubin Observatory, the upcoming legacy survey of space and time. Future missions that will watch, wait, and react. We're preparing, we're ready. And when the next visitor arrives, we won't almost miss it. We'll see it coming. We'll track it carefully. And we'll learn everything it has to teach. So, what have Oumuamua and 2I Borisov taught us? They taught us that the space between stars isn't empty, that our solar system is part of a larger ecosystem, a galaxy full of wandering things, crossing paths, sharing material, connecting distant worlds in ways we're only beginning to understand. They taught us that some visitors are familiar, like 2I Borisov, and others are strange, like Oumuamua, that the universe contains diversity we haven't cataloged, yet shapes we haven't seen, stories we haven't heard. They taught us humility. We thought we knew what asteroids and comets looked like. We thought we understood orbital dynamics. And then Oumuamua arrived and defied our expectations, reminding us how much we still have to learn. But most of all, they taught us to watch, to pay attention, to look up at the night sky and remember that we're not alone, not because of aliens necessarily, but because the galaxy is full of travelers. Rocks and ice, old and young, strange and familiar, all drifting through the dark, occasionally passing through our corner of space. We've seen 2. Soon we'll see dozens, then hundreds. And each one will teach us something new about the galaxy we live in, the systems that surround us, and the ancient currents that flow between the stars. But these visitors, these silent travelers, raise a question that goes deeper than trajectories and compositions. They raise a question about us, about how we respond when the universe surprises us, about what it means to be human in a cosmos full of mystery. In the 7 years since Oumuamua passed through our solar system, scientists have published more than 200 papers about it. 200 papers, thousands of pages, hundreds of theories, models, calculations, debates, all about an object we observed for 11 days, an object we'll never see again, an object that left more questions than answers. Why does this one visitor matter so much? What does our response to Oumuamua reveal about who we are and how we face the unknown? Let's start with the numbers, because they tell a story. Between October 2017 and December 2024, astronomers, physicists, and planetary scientists published at least 200 peer-reviewed papers about Oumuamua. Some focused on its trajectory. Others analyzed its light curve, its acceleration, its composition. Some proposed new theories: hydrogen icebergs, fractal dust, aggregates nitrogen ice fragments. Others challenged those theories, pointing out flaws in the models or gaps in the evidence. Research shows that Oumuamua generated more scientific literature than any other single asteroid or comet in such a short time. Not because it was the biggest or the brightest or the closest, but because it was the strangest, because it didn't fit. And scientists fundamentally are drawn to things that don't fit. Anomalies, outliers, data that refuses to behave. Because that's where discoveries live, in the gaps between what we expect and what we observe. In the moments when nature surprises us and forces us to reconsider everything we thought we knew. Oumuamua was one of those moments, and the response, 200 papers, thousands of hours of observation, endless debates, shows you how seriously the scientific community takes mysteries. But it also reveals something else: how we disagree, how we argue, how we navigate uncertainty when the data runs out before the answers do. Let's talk about the scientific method because it's important here. Most people think of science as a process of proving things, gathering evidence, running experiments, reaching conclusions. And that's part of it. But science is also about arguing, challenging, questioning. When a scientist publishes a paper, they're not saying, "This is the truth." They're saying, "Here's my model, here's my evidence, here's my reasoning. Now, try to break it." And other scientists do exactly that. They look for flaws, they test assumptions, they propose alternative explanations, they replicate experiments, reanalyze data, and publish their own papers saying, "We disagree, here's why." This isn't hostility, it's rigor. It's how science corrects itself, how bad ideas get filtered out, and good ones survive. With Oumuamua, this process played out in full view. Researchers proposed the hydrogen iceberg theory, and other researchers pointed out problems. How long would such an object survive in interstellar space? Could it really remain cold enough to stay frozen? Where's the evidence of hydrogen outgassing? Someone suggested it was a nitrogen ice fragment, like a chunk of Pluto ejected from a distant solar system. Others challenged that, asking how common are Pluto-like worlds? How often do they eject material? Do the statistics support this explanation? Avi Loeb proposed the light sail hypothesis, and dozens of scientists responded, some saying it was worth considering, others saying it was premature, unnecessary. A solution looking for a problem, back and forth. Proposal and rebuttal, evidence and counter-evidence. This is what healthy science looks like: messy, contentious, full of disagreement. But it's disagreement in pursuit of truth. Not argument for argument's sake, but genuine, careful attempts to find the model that best fits the data. Now, here's where things get interesting. Because the Oumuamua debate revealed something uncomfortable: how we balance open-mindedness with skepticism. Science values both. You need to be open-minded, willing to consider new ideas, even strange ones, even ideas that challenge your assumptions. But you also need to be skeptical, demanding evidence, questioning claims, refusing to accept extraordinary hypotheses without extraordinary proof. The tension between those two values is constant. Lean too far toward open-mindedness, and you risk accepting ideas that aren't supported by data. Lean too far toward skepticism, and you risk dismissing real discoveries because they seem too strange to be true. With Oumuamua, different scientists drew that line in different places. Some said the data is ambiguous, so let's consider all possibilities, including artificial origins. We don't have to believe it's alien, but we shouldn't rule it out without evidence. Others said artificial origins are so unlikely that we need overwhelming proof before considering them seriously. And we don't have that proof. So, let's focus on natural explanations, even if they're imperfect. Both positions are reasonable. Both are rooted in good scientific practice. But they lead to very different conclusions. And that's the lesson: science isn't always about finding the right answer. Sometimes it's about deciding which questions are worth asking and how much evidence you need before taking an idea seriously. Let's talk about Avi Loeb again, because his role in the Oumuamua story is revealing. Loeb didn't just propose the light sail hypothesis and walk away. He became the public face of the idea. He wrote a book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth. He gave interviews. He appeared on podcasts. He argued his case loudly, persistently, unapologetically. And many of his colleagues criticized him for it. Not because the idea itself was unscientific, but because of how he presented it. They said he was overstating weak evidence, encouraging wild speculation, and giving the public a misleading impression of what the data actually showed. Some felt he was seeking attention. Others worried he was damaging the credibility of serious searches for extraterrestrial intelligence by associating them with a controversial, unproven hypothesis. But Loeb defended his approach. He said scientists are too cautious, too afraid of being wrong, too worried about their reputations. He argued that if we're ever going to find evidence of alien technology, we need to be willing to consider it even when the evidence is ambiguous, even when colleagues disagree. He pointed to history. In 1054, 80 Chinese astronomers observed a guest star, a supernova, so bright it was visible during the day. European astronomers at the time largely ignored it because their models said stars didn't change. They were eternal, unchanging, fixed in the heavens. The Chinese astronomers, with different assumptions, simply recorded what they saw. And today we know they were right. Stars do change. Stars do explode. And that supernova left behind the Crab Nebula, one of the most studied objects in the sky. Loeb's point: sometimes the consensus is wrong. Sometimes the cautious approach misses the truth. And sometimes you need people willing to take risks, to ask uncomfortable questions, to push boundaries. Whether you agree with Loeb or not, his role in the Oumuamua story is important. He forced the conversation. He made scientists articulate why they disagreed, what evidence would change their minds, and how certain they really were. He didn't settle the debate, but he made it impossible to ignore. Now let's talk about the media, because they played a role too. When Oumuamua was first discovered, news outlets covered it carefully. First interstellar object detected. Visitor from another solar system. Accurate, measured, restrained. But when Loeb's light sail paper came out, the headlines changed. Harvard scientist says Oumuamua could be alien spacecraft. Interstellar visitor may be probe from extraterrestrial civilization. Is Oumuamua evidence of aliens? Some of these headlines were accurate. Loeb did suggest Oumuamua could be artificial. That's a fair summary of his paper. But others were sensationalized, exaggerated, designed to attract clicks rather than inform. They left out the nuance, the could be, the not proven, the we need more data. And the public reading those headlines often came away with a misleading impression that scientists had found strong evidence of alien technology, when in reality they'd found a strange object with an ambiguous explanation. Research shows that science communication is hard, really hard. You need to balance accuracy with accessibility, detail, with brevity, caution, with engagement. And when the topic is aliens, something people care about deeply, something that generates clicks and views, it's easy for nuance to get lost. Scientists noticed this. Some felt that media coverage of Oumuamua was irresponsible, that it encouraged unfounded speculation, and made the public less able to distinguish between solid evidence and weak hypotheses. Others felt the coverage was fine, that public interest is valuable, that getting people excited about science is worth the occasional oversimplification. Once again, reasonable people disagreed. And once again, the Oumuamua story revealed tensions in how we communicate science to a world that's hungry for answers, but doesn't always understand the process of getting there. Here's a question worth asking. Why do people care so much about aliens? Oumuamua sparked more public interest than almost any astronomical discovery in recent years. Not because it was beautiful or dangerous or directly relevant to daily life, but because it hinted just barely at the possibility of contact, of intelligence, of minds beyond our own. Why does that matter so much? Maybe because we're lonely. We've been staring at the stars for thousands of years, wondering if anyone's out there, wondering if we're alone. And we've heard nothing, seen nothing. Found no signals, no messages, no proof. Oumuamua was the first time an object from beyond gave us any reason to wonder. Not because it was clearly artificial, but because it was strange enough that we couldn't rule it out. That tiny possibility, that faint, unlikely chance, was enough to capture the imagination of millions. Enough to make headlines. Enough to spark debates that are still ongoing. It's as if the whole world was holding its breath, hoping that this time, finally, the universe would speak back. It didn't, at least not clearly. But the hope itself reveals something about us, about how much we want to believe we're not alone, about how deeply the question matters. Now, let's talk about what Oumuamua taught us about science itself. The story of Oumuamua isn't just about an object in space. It's about how we respond to mystery. How we build models, gather evidence, test ideas, and navigate disagreement. It's about how we handle ambiguity data that points in multiple directions, questions that don't have clear answers, mysteries that refuse to resolve. And here's the important part. Science doesn't always provide closure. Sometimes the data runs out. Sometimes the object leaves before we're done studying it. Sometimes we're left with competing explanations, none fully satisfying, none definitively proven. That's uncomfortable. Humans like closure. We like answers. We like to know. But science doesn't promise answers. It promises a process, a method for asking questions, carefully testing ideas rigorously, and narrowing down possibilities. Sometimes that process leads to certainty. Sometimes it doesn't. With Oumuamua, we narrowed down possibilities. We ruled out some explanations, we refined others. But we didn't reach consensus. We didn't solve the mystery, and that's okay. That's how science works when the data is incomplete. You do the best you can with what you have, and you wait for the next opportunity, the next visitor, the next data set, the next chance to test your ideas. Research shows that some of the most important scientific discoveries came from unresolved mysteries, anomalies that took decades to explain, data that didn't fit until someone thought of a new framework, a new model, a new way of looking at the problem. Maybe Oumuamua is one of those. Maybe someday someone will look back and say, that was the clue. That was the moment we realized something profound about the universe. Or maybe it will remain a mystery forever. A strange visitor that passed through, asked questions, and left before we could answer. There's a deeper lesson here, one that goes beyond Oumuamua. It's about how we live with uncertainty. We live in a universe that doesn't owe us explanations. Stars explode without warning. Comets appear from nowhere. Objects tumble through our solar system, strange and silent, defying our expectations. And we, curious, pattern-seeking, meaning-making creatures, try to understand. We build telescopes, we measure, we calculate, we argue and debate and publish papers, all in pursuit of truth. Sometimes we find it, sometimes we don't. But the search itself, the willingness to ask questions, to confront mystery, to admit when we don't know, that's what makes us human. That's what makes us scientists. Oumuamua reminded us of that. It showed us that the universe still holds surprises, that even in an age of advanced technology and sophisticated models, nature can still baffle us. And maybe that's a gift. Maybe the mystery is more valuable than the answer would have been, because it keeps us humble, it keeps us curious, it keeps us looking up, wondering, asking what else is out there, what else have we missed, what else is tumbling through the dark waiting to be seen. The search continues, not because we have answers, but because we have questions. And as long as the universe keeps whispering mysteries, we'll keep listening, wondering what it's trying to tell us about the vast, strange, beautiful cosmos we call home. But there's one question left, the simplest and perhaps the most profound. Where is Oumuamua now? And what does its journey tell us about endings, beginnings, and the quiet persistence of things that travel alone? Right now, at this very moment, Oumuamua is still out there. It's beyond Neptune, beyond Pluto, beyond the Kuiper Belt, moving at 26 kilometers every second, tumbling silently through the outer darkness of our solar system, heading toward a place it will never truly leave behind. And in about 20,000 years, it will pass near another star, then another, forever traveling, forever alone. Let's do the math because numbers tell stories. When Oumuamua was discovered in October 2017, it was about 33 million kilometers from Earth, roughly 85 times the distance from Earth to the Moon, close by cosmic standards, close enough to study just barely. By December 2017, it had moved beyond Jupiter's orbit. By mid-2018, it crossed Saturn's path. By 2019, it was passing Uranus. By 2020, Neptune. Today in late 2024, Oumuamua is approximately 6 billion kilometers from the Sun, about 40 times farther than Earth. It's moving through a region of space we've barely explored, a cold, dark frontier, where sunlight is 1,000 times dimmer than it appears from Earth. It's too faint to see now. Even the most powerful telescopes on Earth can't detect it anymore. The light it reflects, already weak when we first spotted it, has faded beyond the threshold of visibility. We'll never see it again. Never track it, never photograph it. It exists now only in our data, our models, our memories, but it's still there, still moving, still tumbling at the same rate, 7.3 hours per rotation, that it was when we first measured it, still carrying its secrets into the dark. Research shows that Oumuamua will take about 20,000 years to travel 1 light year the distance light covers in a single year. It's moving fast by human standards, but slow by cosmic ones. Space is so vast that even at 26 kilometers per second, the journey between stars takes millennia. In 20,000 years, Oumuamua will pass within a few light years of the star Ross, 154, a small red dwarf in the constellation Sagittarius. It won't stop, it won't orbit, it will just drift past a silent visitor in someone else's sky if anyone's there to see it, then it will continue. Past Ross, 154, past other stars whose names we don't know, whose planets we've never seen, tumbling through the Milky Way, slowly circling the galactic center, along with billions of other stars, rocks, and wanderers. It will take 225 million years to complete one orbit around the galaxy. By then, Earth will be unrecognizable, species will have risen and fallen, continents will have shifted, the sun will be older, brighter, and Earth, if it still harbors life, will be warmer. Stranger nothing like the world we know. But Oumuamua will still be tumbling, still moving, still carrying whatever it is, rock, ice, relic through the endless dark. Think about that journey for a moment. Think about what Oumuamua has seen and what it will see. Before it reached us, it traveled for hundreds of thousands of years, maybe millions. It drifted through regions of space where the nearest star was light years away, where darkness was so complete that even the Milky Way was just a faint smudge across the void. It passed through molecular clouds, vast nebulae of gas and dust, cold and silent where new stars are born. It might have witnessed stellar nurseries, places where gravity pulled matter together and ignited fusion, lighting up the darkness for the first time in millions of years. It might have passed near other planetary systems, worlds we'll never see, orbiting stars we'll never name. Maybe some of those worlds had life. Maybe some had civilizations looking up at their own skies, wondering if anyone else was out there. And if they had telescopes, if they were watching, they might have seen Oumuamua pass by just as we did. A faint point of light moving wrong, tumbling strangely. They might have wondered what it was. They might have debated, speculated, written their own version of 200 papers trying to explain the visitor from beyond. Or maybe no one saw it. Maybe it drifted past in silence, unnoticed, just another rock in an ocean of darkness. We'll never know. Oumuamua carries no record of its journey, no log, no memory. Just the scars of time, its red-weathered surface baked by cosmic rays, a testament to age and distance, and the slow erosion of matter in space. Here's something worth considering. Oumuamua is not unique, not anymore. Since 2017, we have discovered other interstellar visitors. We have learned that objects like Oumuamua pass through our solar system regularly, maybe several every year. And we've realized that the galaxy is full of them. Trillions upon trillions of rocks, ice chunks and debris all ejected from their home systems, all wandering through the void, all following paths that will take them past, stars, planets, and worlds they'll never know exist. Scientists estimate that there are more interstellar objects in the Milky Way than there are stars, more wanderers than suns. A vast, invisible population of travelers drifting silently between the points of light we see in the night sky. Oumuamua is just one among countless others, one brief glimpse of a universe-wide phenomenon we're only beginning to understand. And that's the profound realization: we don't live in an isolated solar system. We live in a crossroads, a place where paths intersect. A cosmic highway where travelers pass through constantly, most unseen, most unknown, but always there. Our solar system isn't a lonely island in the dark. It's part of a network, a slow, ancient exchange of matter that connects every star in the galaxy. And Oumuamua reminded us of that. It reminded us that the space between stars isn't empty, that the universe is full of motion, full of journeys, full of things that travel alone, but are never truly isolated. Now, let's talk about endings and beginnings. Oumuamua's visit to our solar system was brief, a few months from entry to exit, 11 days of useful observation, then silence. But its impact will last much longer. It changed astronomy. It forced us to build new telescopes, develop new strategies, and rethink our assumptions about what's out there. It inspired missions like the Comet Interceptor, designed to chase visitors we haven't seen yet. It motivated funding for projects like Breakthrough Listen, searching for techno-signatures we might have missed. It sparked debates that are still ongoing, questions that remain unanswered. Research shows that some of the most important discoveries in science come from anomalies, things that don't fit, things that challenge our models, things that force us to look harder, think deeper, question more carefully. Oumuamua was one of those anomalies. And whether it was a rock and iceberg or something stranger, its legacy is clear. It showed us we're not done exploring, not done discovering, not done being surprised by the universe. Because here's the truth: the next Oumuamua is already on its way. Right now, somewhere in the darkness between stars, another object is tumbling toward us. Maybe it's similar to Oumuamua. Maybe it's completely different. Maybe it will answer the questions the first one raised, or maybe it will ask new ones. We don't know, but we're watching, we're ready, and when it arrives, we'll do what humans have always done. When confronted with mystery, we'll study it, we'll measure it, we'll argue about it, we'll try to understand, because that's who we are. Curious, persistent, unwilling to accept ignorance when knowledge might be within reach. Let me tell you what Oumuamua means in the end. It's not about aliens, it's not about light sails or hydrogen icebergs or any specific theory. It's about the fact that the universe still surprises us, that even in an age of satellites and supercomputers and models refined over centuries, nature can still show us something we've never seen before. That's humbling, that's beautiful, that's what keeps science alive. Oumuamua reminded us that we live in a universe larger and stranger than we imagined, that the space between stars is full of travelers, that every solar system is connected loosely through an exchange of matter so slow and vast that we've only just noticed it. It reminded us that mystery is not a failure of science, it's the fuel that drives it. The questions we can't answer are the ones that push us forward, that inspire new ideas, that force us to build better tools and think more carefully. And it reminded us that some journeys have no clear ending. Oumuamua didn't solve its own mystery. It didn't leave us with answers. It left us with wonder, with curiosity, with the knowledge that more visitors are coming. And maybe one of them will tell us something profound about the galaxy we call home. So, where is Oumuamua now beyond Neptune, beyond visibility, beyond reach, but not beyond memory, not beyond influence, not beyond the quiet legacy it left in the minds of everyone who watched it pass? It came from somewhere we can't name. It traveled for longer than human civilization has existed. It passed through our little corner of space for a heartbeat of cosmic time, and then it left carrying its secrets with it, heading toward places we'll never see. It asked more questions than it answered. It sparked more debates than it settled. And in doing so, it did something remarkable. It reminded us that the universe is not a solved puzzle. It's a living mystery. And we, small, curious, persistent, are part of it. Every night when you look up at the stars, remember you're not just seeing points of light. You're seeing the destinations and origins of countless travelers. Rocks like Oumuamua tumbling through the dark visiting solar systems, passing by worlds carrying stories we'll never hear. Some of them pass through our sky. Most we miss, but they're there. Always moving, always traveling, always reminding us that space is not empty and we are not alone in watching the night. Oumuamua is gone now, too far to see, too faint to track, lost in the vastness. But somewhere out there, it's still tumbling, still spinning every 7.3 hours, still reflecting sunlight too dim for any telescope to catch, still following the path that will take it past other stars, other systems, other worlds. Maybe someone will see it 20,000 years from now. Maybe they'll wonder what it is, where it came from, what it means. Maybe they'll write their own papers, build their own theories, have their own debates. Or maybe it will pass unseen as it passed unseen for hundreds of thousands of years before reaching us. Either way, it will keep moving, keep traveling, keep carrying its silent story through the galaxy. And we'll keep watching, keep wondering, keep looking up at the night sky, hoping that the next visitor will arrive soon. Because that's what Oumuamua taught us in the end. Not answers, but hope. The hope that the universe still has secrets to share, that we're part of something larger, that the story isn't over, it's just beginning. Thank you for drifting with me through this quiet journey. Thank you for wondering, for questioning, for sitting with mystery instead of demanding easy answers. Oumuamua's story is our story, a story about how we face the unknown with curiosity instead of fear, with humility instead of certainty, with wonder instead of indifference. The universe whispered something to us in 2017. We're still trying to understand what it said, and maybe that's okay. Maybe the whisper is enough. There are more stories waiting in the darkness, more visitors, more mysteries, more moments when the cosmos reaches out and touches us, brief and strange and unforgettable. Stay curious, keep watching the sky, and when the next traveler arrives, we'll explore it together. Sleep well. Dream of distant wanderers. Good night.